All right, so let's get started. I didn't hear what the introduction said. If it was wonderful, it's all true, and if it was awful, it's all scurrilous lies. So let's get the talk started with an edit being done right at the beginning, and that is I probably should have more correctly titled this being a semi-historical reflection on self-assembled monolayers of thiolates and metals as a form of nanotechnology. It's really nice because I get to revisit a lot of things that I haven't thought about in a long time, going back looking at the stuff from the old days. And I want to point out that it really is amazing to be able to be here and talk on behalf of such incredible people, George and Dave, and it's like both an honor and humbling to represent them in a meeting such as this. So. Big shout outs to them, and I'll try to correctly indicate contributions coming from a lot of really fantastic collaborators along the way. But we get right back to the beginnings of this and what was the inspirations and origins. And I always go back to the point that I was hired at Bell Labs originally back in 1980 based on some work I did that was principally directed, not in terms of what the bulk of my thesis research was, but a little bit that happened at the end that was directed at trying to understand the properties of wetting and adhesion involving organic materials, in particular polymers. And this picture that's shown here is one of a drop of liquid. It's actually sitting on a fairly complex substrate which contains microstructured features that pattern regions of hydrophilicity and hydrophobicity. If you see how drops move along surfaces like this, they have very complex patterns of hysteresis that reflect the characteristic textures that are present in different surface interactions. And even like in a simple case like this, that there's enormous complexity that emerges from systems of this sort. And this is actually something that I can show you here in a little bit more detail in terms of the work that we actually did at MIT back in the late 70s looking at surface functionalized polymers. There's two pictures of substrates that embed certain levels of heterogeneity in what's present at the interface, shown as like squares and black circles. And in particular, if we have a surface modified polymer, which was a material that we had studied in some detail, the polymer being in this case polyethylene, chemically derivatized to be hydrophilic at its surface. These materials could restructure in ways that led to enormous complexity, and what's shown is changes in wetting data, the contact angle as illustrated by the drop that I showed you on the slide before, as a function of temperature and time. And you'll notice that the surface properties change relatively abruptly, going from hydrophilic to hydrophobic, extremely hydrophobic, even heating at a modest temperature for a brief period. And the really interesting part is if you look at the chemical composition of this as determined by a surface-sensitive spectroscopy, the composition hasn't changed at all, at least not detectably by those kinds of techniques such as X-ray photoelectron spectroscopy. And the picture that emerges from data like that is that at the nanoscale, there's a structural characteristic that leads to the wetting behaviors that you see. And it's entirely determined by things that are in very proximal direct covalent or molecular contact, and that is there's the bulk material and there's the ambient environment, which would be whatever is contacting that material at its interface. And that at the nanoscale, like at the level of the length scales of molecular interactions occurring at that length scale, there's a perturbed region, and all the complex properties of that system emerge because of the nature of that perturbed region. And we did a lot of work trying to understand systems like that. And as a graduate student, you don't like to do a lot of work and then not graduate. So eventually I did graduate, so there was an off-ramp for that. But we never really got very close to the goal of modifying materials like that in a way where they would be a really good and easily understood model of the underlying structural correlations that underpin the macroscopic physical properties seen. And even if the property one is looking at is the simple case of just a wetting behavior with a contacting fluid. And so we needed a better model system. And, and ideally it would be flexible in that it would tolerate a broad range of functional groups, so you can broadly, survey the depth of molecular interactions, and bonding characteristics. It should be simple, because you don't want to have heroic chemistry being required to do the process. And it has to be able to provide the characteristic structure property correlations that you're interested in. And at Bell, fairly early on, we arrived at a model system, and this was, jumping ahead, looking at a lot of data that was eventually put together, to describe the system. But this model system was SAMS, and we didn't start with the level of sophistication that was shown in this picture, but this is like to get ahead of the story, to give you where the outcome was. And that is, we had a substrate, and I apologize for the fact that I'm not able to point with a pointer because it doesn't work in this context, so I can't do that. So you have to use your imaginations as best you can, that I'm actually pointing at the relevant part of the screen that you're currently looking at. And so anyway, what you see is an underlying metal substrate that shows the interaction of a functional group, which is labeled here as the ligand or head group. And in the terminal functional group is where all the interesting parts that are expressed at the interface necessarily go. And then in between is that organic interface, which has the nice feature that it spaces the one part of the physical interaction from the other part. And if those characteristic functional groups have orthogonality in terms of how they bind at various interfaces, you can arbitrarily organize. And that's where the word self-assembly comes in, because it's driven by the characteristic balance of all the molecular interactions that are present. The pairwise interactions of nearest neighbors, and the characteristic metal substrate bonding interactions, and the interactions with whatever is the contacting ambient phase that expressed at the organic interface of this material. And out of that comes a characteristic structure. And it turns out that the systems that we looked at also had the attribute that they turned out to be, in the simplest cases, highly ordered materials. In fact, one's embedding crystalline order, right? And that's actually shown in that cartoon in a fairly nice way. And I think the point is, and as George called out in a slide that I found in his massive slide decks as I went through a box folder that he sent me, this slide here, which is really a nice summary of why this was a great idea and an impactful idea. And that is, it's kind of inevitable, that it's a structure that exists somewhere in between the molecular scale and the much more macro world. And we didn't have nano at the time when we were first talking about this, but it was, we used to call this mesoscopic, that it was like somewhere of a size that was relevant to the length scale of where interesting things happened, And these characteristic dimensions are interesting, but they're also very challenging. That they're like of the order or of what's important for interactions involving living materials such as cells. They're smaller than the wavelength of light, and they're comparable to the scattering lengths of electrons and excitons, and small compared to for example, grain boundaries, et cetera, right? And if you look at the underlying phenomena that could be impacted, you find implications related to problems involved in biology, electronics, photonics, and what I'm going to try to do in this talk is to not really speak in detail about any of these things, because you can't do justice to it, and I'm trying to work my way through some sort of snapshot picture of more than 4 decades of work by a lot of people, and in particular, Dave and George, the enormous contributions that they made, and a few of my own as well. But also, there's this world of adoption that's happened. There's a reason why there's tens of thousands of papers in this field, because people have found all kinds of ways to make this useful in their own work, and that accessibility for these broad area of applications is really important. So there was a first paper, and we actually started in on this work. I think I did the first experiment, that was with my hands in 1981 or thereabouts. And we did a rather important and prophetic patent related to this work. And the first publication itself was this one that appeared in JACS in 1983. Early 1983, and it lays out the basic ideas of what we were looking for SAMs, and we didn't have the word SAMs at that time either, so that's not in the title, so there's obviously evolution going on here, and you can see that it's talking about that we're really interested in in things that involve interactions, molecular interactions at ambient interfaces with relevance related to lubrication, tribology, electrochemistry, electronics, and photonics, and electrical conduction. All words that were really interesting to the phone company, because this was a Bell Labs, effort, right? And but we also threw in, biological membranes, which was actually, inspiring, the part of the self-assembly part of this story. So you had to kind of do that sotto voce at the phone company. We didn't do molecular biology, at least not in my department, which was a department that was concerned with mechanisms of adhesion, because we glued a lot of things together. Okay, so, but we do the first experiments, and that begets what I call, my first experience with the now what moment. I did an experiment, and the properties of a gold film that I immersed in a particular adsorbate solution changed remarkably. And then now what? Like something happened, and the properties were such that you knew something that was a really, hydrophobic thing had formed at that interface. But beyond, that gross characteristic, what was it? And so there had to be a lot of what we now would call multimodal means of characterization invented to really characterize these materials in detail. And this is like such a huge part of the story, because circa 1980, that didn't exist. And if I was there in person, I was actually going to pull out, and I'll try to do that with my backpack being over there, a piece of data which illustrates the characteristics of the problem, that we were, recording things with, machines that used the, first generation so-called microcomputers, which was the, in the space of Data General and, and DEC type computers that were gigantic, in the sense that they had 64K of RAM, and something on like that. But you had to put it together with a whole bunch of stuff. So, for example, the incomplete list of items in this recipe were things like ellipsometry, XPS, reflection absorption infrared spectroscopy, microscopies, X-ray methods, for example, to characterize the crystallographic textures of the substrates that were actually present, because when you evaporate a gold film, do you actually know what the crystalline form of it is? So there's a lot of things that you figure out, and there's other things shown on here. For example, low energy electron diffraction, which provided an important early lead as to the characteristic order that were present in these systems. And of course, because they were easy to do, we always measured wetting and contact angle data. And I have some names at the bottom of this slide that call out people that have made particularly important contributions to a lot of the parts of the story that were there. But the starting point, I think, always was looking at correlations associated with wetting and correlated with a more chemical-specific surface spectroscopy, X-ray photoelectron spectroscopy, how things scaled because we didn't understand anything. We approached this as a problem in physical organic chemistry. And I always made the joke that what you do when you have a really complicated problem involving something that you don't understand, get another thing that's really complicated that you don't understand and divide them, and what emerges from that is an understanding of this thing that was so mysterious, and so that's where that's another way of saying structure property correlations, and that's what's like shown here. As a function of chain length, how does the contact angle change? And you see behaviors like for different metal substrates, gold, silver, copper, that as a function of the chain length of an N-alkane thiol, the contact angles, with water and hexadecane approach very hydrophobic and very oleophobic limits, very rapidly. And what you're seeing is that the underlying substrate is being shielded from the contacting fluid by the presence of this molecule. And you see a characteristic scaling, for example, of core level data that shows that the photoelectrons associated with the metal substrate are being attenuated. And from that, you can get an idea of what the thickness is of the layer that's present. So the contact angle data is showing that this is a very coherent organic monolayer, and because it's oleophobic against the hydrocarbon not wetting a hydrocarbon, it says that it's a very special organization. And that's actually a really important clue. And of course, from the XPS data, you get an idea related to coverage. But we really wanted more than that. We wanted structure. And one of the really important impacts came from doing infrared spectroscopy, and it's shown here in red, reflection absorption infrared spectroscopy. This is where I think one of the spectacular contributions that Dave made to this problem really came into play. Because early on, people thought this was a really interesting and possible kind of measurement, and one that had been discussed in the literature, but with the characteristics of instrumentation that was available at the time, would be essentially impossible to do. And there was a lot of really important technical bits that had to be worked through to be actually able to do this. Because like in this generation, these instruments were not completely digital. They involved a lot of analog circuitry that was associated with how the interferometer in the instrument actually worked, and digital amplifiers, as exists now, didn't exist at that time in the same way, and A to D converters didn't exist in the same way as they do now back then, and so like every aspect of it was new, and getting it to work was an enormous contribution. And the thing that's actually interesting is that in yellow, in that upper right-hand box, you see a characteristic spectrum of an N-hexadecane thiol monolayer on gold. And it doesn't mean anything to a bunch of people, but there's like all kinds of like interesting parts in this when you get into the details of the spectroscopy. And one of it is that it has enormous optical anisotropy associated with it, in the sense that the characteristic band intensities associated with the methylene parts of the molecule structure are actually relatively weak compared to the methyl group. There's only one methyl group, and there's 15 methylenes. Beer's law should kind of work in an isotropic medium. And the point is what it's saying is that there's special projections of these functional groups in the optical axis that's defined by the metal substrate. So when you're doing a reflection experiment, the graph that's shown in the lower right-hand corner illustrates that the only intensity that you see comes from projections in the surface normal direction for an incident beam of infrared radiation along a grazing angle of incidence. And if you understand this in quantitative detail, and the picture at left, shows the way you have to do this. You have to look at, what's the incident input angle for the radiation, what's its frequencies, the bandwidth associated with it, what's the underlying complex optical function of the substrate materials and its many layers, right? And then apply the laws of physics where you think about both the absorption coefficient and refractive index and their wavelength dependencies, and you can come up actually with a structure associated with the kind of spectrum that you see in the yellow box. All right, and this was actually something that Dave provided an early test bed with for a model system that had been characterized in the literature in earlier years, and that is fatty acids on an aluminum substrate that bearing a native oxide overlayer. And I love the slide, the box that's on the left-hand side, which shows corresponding lipsometry data. I was personally told by a very influential person that this measurement was impossible. Okay, and if you notice how many data points are on this are in that plot, it's actually there not because we're driven or we were driven by a desire for high confidence levels, like 3 sigma or something like that, or it's not a physics problem, right? 5 sigma or something like that. It's there because it's it's kind of like a New Jersey thing, and because the slope of the line above the dashed line is the dimensions of the methylene group. Okay, so it actually says that there's something amazing that happens in this material, and it actually shows that the controversy that was in literature as to whether these films are disordered or ordered, actually reflects the experimental difficulty of actually preparing these films, because the substrates tend to contaminate in the ambient environment, and you're doing chromatography, sticking things down, and if you have any kind of impurities that are present, they may actually adsorb more strongly than the molecules you're interested in, and that complicates the data and the organizations that'll emerge from an assembly process. And you see that in the IR data that's shown on the right. You can characterize those optical anisotropies that are shown in the experimental spectrum in terms of a theoretical spectrum for that mass coverage of material at an isotropic distribution relative to the underlying substrate. What it would look like, and compare that to what it actually looks like, and from intensities and band positions, and actually measuring intensities quantitatively, come up with a structure. Okay, and that's actually what was done. And this is a diagram showing the more detailed structural model with all the details that have to go into doing that, and attributes of structure that came out of that first foundational study. For example, whether or not the carboxylate group bonds to the interface via a structure that's bidentate with C2V symmetry, or a distorted version of that, which you get from the characteristic intensities of the symmetric and antisymmetric carboxylate stretching vibrations. It's in deprotonated form, etc. And then we start talking about things related to how the bonding group directs the chain, how the chain assembles to pack hydrocarbon to hydrocarbon, in a self-association, and ultimately what winds up to be the projection of the functional group at the ambient interface. And you notice that the functional groups that are shown in this model case are ones that don't perturb bonding of the head group, right? Because you can't be polar in this case because the underlying substrate is polar. And this was like a really remarkable outcome, and it just shows just how profound an achievement that came out of Dave's contributions in making this a quantitative, structurally determinate form of spectroscopy. And here's data that shows, for example, these structure property correlations associated with SAMs on a variety of substrates. Copper, silver, gold. That was one of the series that we went through, the assembly on the coinage metals, as we called it, in that paper. And you find, as a function of chain length, that you have a similar structure, and it's kind of like a beautiful thing that you can then go ahead and reduce that to a set of arguments as to whether or not the chains are along the surface normal direction, or do they have a slight cant from the surface normal direction. And when we found, for example, that they have a cant off the surface normal direction, which is larger on gold than it is on silver. But in gold, that orientation is fixed. It only goes in one direction, so you see a sign of an angle there, where chains are rotated azimuthally and then tilted. And we call these alpha and beta as the characteristic angles of the single chain structure. And they only go in a certain direction on gold, and that makes a determinate projection of the methyl group at the chain end at the ambient interface. And but how do we know? Because it wasn't agreeing with quantitative calculations as to what was happening with the intensities of those methyl groups, and I realized that we were only measuring even chain lengths, and part of the magic of physical organic chemistry is that we don't understand that exactly, so we've got to get an odd chain length, which we don't understand either, and take the two of those and compare them, and then we'll understand everything, right? And when we did odd-even, you see odd-even progressions in the intensity ratios that correspond to that fixed angle, right? Because in one case, the methyl group will point this way, and in another case, it'll point more along the surface normal direction for a fixed angle of tilt. And in gold, that's true, and on silver, that's not true. And that's actually an interesting part of like how these metals differ, but the whole point that I'm saying is that you're making this sound like a really complicated story that's emerging in a relatively direct way from this characteristic spectroscopy. And there's like more that comes to it as well, and here's like a lot of what I will leap through, just kind of like bypassing all the hard parts that went into doing this. But like we find that there was a corresponding registry, at least in the simplest measurement that we did, that's showing this overlay of sulfur atoms in chains on top of the hexagonal lattice of a gold 111 substrate. And the reason why it's gold 111, when you evaporate the film, maybe you have everything, but it turns out that a thermal evaporation produces a really strong fiber texture. So most of the grains that you have are presenting with a 111 orientation, very strongly so. And you can actually manipulate that as part of the procedures that you use for preparing the underlying substrates. And the chains organize on that, but it also turns out that the chains organize based on their pairwise interactions. The lateral interactions drive another level of organizations in materials. And it was also clear from the data that's shown here that pairwise interaction involve an underlying orthorhombic sublattice that involves chains oriented at 90 degrees relative to one another. And that's where I would have passed around in the audience. This is precious, okay? This is you'll not be able to see this. This is actually a spectrum that was plotted in 1988, okay? That was measured looking at a hexadecane diol monolayer on gold 101 single crystal, looking at the methylene bending vibration at 100 Kelvin, right? So this was actually the most complicated IR experiment that we did back in that day. Brilliant contributions from Larry Du Bois making it possible to do this in conjunction with the diffraction measurements to establish the root 3 structure at the gold substrate, or at least an element of the root 3 R30 degree overlayer structure, and the orthorhombic sublattice, which is shown by the factor group splitting that shows up in those bands, that they have to have the two methylene groups interacting at 90 degrees, and that's a splitting of the degeneracy of that vibration that comes from that underlying texture. So we know a lot of stuff now, right? And it turns out that this is like a never-ending story. Just like as the scope of substrates that go up, the complexity of the story goes up. So like, for example, SAMs on gold, it actually was a much bigger unit cell than the one we saw from that first order data. And that's shown in the panel that's on the left-hand side of this slide. And as you go up on things like silver, turns out that's a different overlayer, and that overlayer actually reflects assembly on top of a sulfide interface because the substrate actually activates the molecules, and it's not assembly on the metal itself, but it's assembly on a monolayer level metal sulfide that has a root 7 characteristic structure, so I'm speaking in jargon here. And then you can go to things like, for example, the picture that's shown on the bottom right-hand side is the characteristic structure associated with assembly on gallium arsenide 100, which is a much more complicated substrate to deal with, and so on and on, and people have worked this in grisly detail in the literature. But what remains is the story of the ambient functional group, because that's why we're doing this, right? And so I put the plot that's shown. I put the graphic that's shown on the upper left-hand quadrant. That was done by my by another close collaborator, Larry Du Bois, to show, what these modalities were, and confirmed by things like even, really hard measurements like, helium diffraction studies, which actually only probe the ambient methyl interface. And to actually show, for example, like thermal behaviors that correspond to how these layers melt when you have a canted structure. They're tilting because the lattice spacing is larger than the dimensions of the chain. And so the chains tilt to maximize their lateral interactions. And when you heat them up, they melt, but they don't melt uniformly. They melt from the top down. And this is confirmed by really complex measurements such as helium diffraction and lead measurements, but also for example in theory that as done by Michael Klein, and there was a really a beautiful story that emerged, and the underlying motivation that was original to this work was to have these ambient functional groups not just be low surface free energy things like methyl groups, but rather a much more articulated set of functional interactions. So that's the part of the story I want to turn to now. And I want to just actually point out that I think a big impact of SAMs has been expressed in the now almost impossibly gigantic literature associated with nanoscale colloidal particles, which the kinds of ideas that we did on two-dimensional surfaces play into the three-dimensional context of those materials, but in a manner that's consistent with the truncation planes associated with those small particles, where you don't have a single crystallographic texture, but rather maybe a variety of low index planes that terminate its finite scale. And of course, modifying materials with organic functionality in a way to make their properties beneficially exploitable in a desired context. For example, as emissive materials, as photonic materials, as labels for radiographic diagnostics, et cetera. And I can't go into that because it's too vast a literature and it's not mine. So we'll move on and go back to the original story again. And that is, we have a modifiable interfaces and we can show. And I think the picture at the bottom was from George originally. The earliest example of a patterned substrate in which half the wafer was dunked in something that's hydrophilic producing SAM, and half of it dunked into something that's the hydrophobic side. You see the drops placed on it show different contact angles for these water drops in contact. And it was actually the way in which you can actually study the pH dependence of the contact angle in cases where you have proton being donated, as a function of pH change, right? Like what's the effective pKa of the interface, and what kind of perturbation exists as a function of like what the composition is, because you make mixed compositions, with hydrophobic and hydrophilic, et cetera. And it was so you get this really beautiful functional surface chemistry story that emerges from it. But the picture actually shows that this should be printable, right? Because if you can pattern it by dunking half and half, maybe there's like a better thing to do. I wish I could say that thought occurred to me, but it didn't, okay? And there's like a reason why we want to pattern things, and it's inspired by the great complexity, but the enormous sophistication of what's done in high-performance microelectronics. And the bottom line is you can do things, and this is thanks to Paul Weiss for this slide. You can do things with atomic precision that are enormously difficult to do using STMs as the way to move, atoms around on, for example, on a copper substrate to get quantum corrals, showing up, with perturbations of electronic structure that are at the atomic scale, and that's like a really incredible experiment. Or you can do microelectronics, which are, I would argue, even more complicated than the example shown on the left-hand side. But I think Paul thinks it's more accessible in the middle, but it's more accessible because of a fantastically complicated and enormously expensive infrastructure of equipment and machines and tools that let you make things like those that exist in integrated circuits. And the fabs are things, as we know currently, that are that have costs associated with them that correspond to like GNPs of a small country, And so, so it's enormously sophisticated, but it's like enormously expensive. And the thing that we loved about SAMS and was motivating about it is that assembly, drives the formation of structure, which is thermodynamically directed, and maybe that's useful somehow, right? But then imposing a level of patterning on it, maybe we can get into this world which is directly impacted by photolithography, which is saying that, rather than doing exposures of resist, et cetera, which are then forming the latent images that are transferred to materials, maybe you can do that more directly with the molecules themselves. And there's a reason why you want to do that, is like I mentioned, the tool sets for photolithography are enormously expensive. So this is an exposure tool, okay? And this is, 193 nanometer exposure tool with immersion optics that now produce like the 7 nanometer feature lengths that are associated with current state-of-the-art devices. Wonderful, not something to have in your own lab because you could never afford it. And it would always be broken, especially if you let students touch it. Okay. All right, and the patterning part is this tremendous contribution that George brought forward related to microcontact printing, and that's like shown in this characteristic set of images here that have just this enormous graphical beauty associated with it. So fine design rules associated with this kind of printing, where you print a SAM and use that latent image in the printed SAM as the etch resist for etching the gold substrate, okay? And the one that's shown at right is also a really nice one in the sense because it was also said by a person who shall remain nameless that this was impossible, okay? What the quote was, show me one example of a latent image in a molecule that's transferred into a thin film structure, okay? And the reply is regarde, and and some beautiful pictures showing like for example the use of a pattern stamp, right? And that's the part of this, right? The stamp in this case is an elastomer, a silicone, which is patterned by molding. And the patterning of the stamp is done actually just using a printed grayscale mask that's done on a transparency, okay? And so it was actually a fairly simple set of operations that allow you to make stamps at the microscale that do print molecules and then do stuff with that, right? And shown here as an etch resist. And so, a lot of work to show what kind of structures you can make, what are the limiting feature sizes. Obviously, a really complicated part of this is that as you go up in size, and you want to stitch pieces together, how can you do that with registration, right? And what other kinds of extensions can you envision? So this is what we call soft lithography. So printing was the first version of it, but there's actually others. So for example, you can do molding steps, and so for example, if I place the stamp down on the substrate, I can actually use that as a soft mold to pattern another material, such as, for example, a resist or a fluid. And the applications that come out of that are direct forms of patterning based on fabricated curable polymers, which you could say as a thicker resist. But it actually also was the definition of a way of approaching doing microfluidics in a new context. So you can see the footprint of applications is starting to spread almost explicitly. And because you have stamps that are articulated in their thickness, and articulated in their thickness at wavelengths that approach, for example, the sub-wavelength regime for light in the visible region, you can use them as phase contrast masks rather directly, right? So they can actually be used in lithographic settings. They can be used as printing tools. They can be used as a molding tool, and you do stuff with it. And so this is a really beautiful picture of one of the first really high-end applications that came out of the work by John Rogers and his collaborators at Bell Labs, actually doing the full fabrication of an active matrix display backplane that involves, in this particular case, gold bus lines in electrodes that define the channel lengths for a printed organic semiconductor. So these are organic TFTs in conjunction with the metal parts, and all done by these soft fabrication methods. Okay. And this picture shows like other things. Like, so for example, if you look at this, the box at the bottom that shows that helical coil, that's actually a grating that's printed on a fiber optic, by using like a rotating printing tool that lets you do a circumferential patterning of the resist level. And obviously something that you could only do with great difficulty by a projection lithography approach, which is something that does printing in 2 dimensions most beneficially, but in 3 dimensions would be much more complicated. So all kinds of like cool stuff, right? And it's an ongoing story. But let's actually look at other enabled applications. So this picture shows, if I can do printing, I can do printing in a way that what I print can either be a resist level for an etchant, or it can be a resist level for the absorption of other molecules, right? And you get orthogonal assembly that occurs in that case. And so this is an example of a deeply exploited model where the arrays that are printed carry things that elicit specific backgrounds that resist biological molecules of diverse form, in particular proteins and serum proteins, et cetera, in complex bioanalyte solutions. But also allow you to put in explicit recognition elements that will bind to particular things that you want to select from a complex background. And that's what's shown on this slide in cartoon form, where like, for example, the one shown on the left is one of the best binding systems known, which is biotin as a binding target for streptavidin. And this has been deeply exploited. And an interesting part of the story is, like, if you make things like this, what's the I/O for the experiment? Like, how do you get information out of it after you've done the molecular architecture that's associated with it? And that's where like a really interesting part comes in. Like, for example, you could do spectroscopy, you can do electrochemistry, so you can use electrons, photons, method X. And method X, as has become now well understood, could be things like plasmonic responses, which are particularly well enabled to be engineered in this context with devices of this sort. And stuff like this was one of actually the earliest commercialized applications of SAMs, involving, for example, the complex but highly effective inert background, right, that the biological part of the recognition can be written against. Okay, and this is like a part of the story that actually gets to be rather interesting, because you don't have to just do like recognition of proteins, but you can actually bias much more complicated structures. So this thing that looks like an apple pie is actually supposed to be a depiction of a cell binding to a targeted materials that are placed down using an orthogonal resist, that there's something that resists the protein absorption, and this, like, for example, fibronectin, that promotes specific binding of a cell. And here's an example of SAMs that resist protein absorption. You notice that they have characteristics that of various levels of charge, or the lack thereof, but they all basically promote osmotic repulsions as the mechanism for avoiding the absorption of protein. Okay, and what's beautiful about this is that you can then go ahead and do really neat experiments that show, like, for example, how a specific target molecule will impact binding of a cell, and that we can then put a specific compound, what's shown here is Taxol, impacting the spreading of those cells as a function of the solution phase concentration. And so the SAMs in this case define a starting point for this outcome, and the cells then proliferate along it, and then we can do perturbations in the background and look at how those chemical perturbations actually modify the development of a more tissue-like structure in that case. And this is actually one of the coolest things I think that was seen. For example, like, what's the length scale of patterning that impacts whether or not a cell is happy or not happy? And this is one of those great contributions from George's lab. For example, they can have a thing that's like of the order of a portion of the cell size, but yet a little bit too small, and the cells attach, but they're unhappy, and they rapidly decide that they want to die, right? It initiates an apoptosis response. And then you then go to something that's bigger. The cell is happy. It adopts the contours of that. You get polarized structures in the cytoskeleton. And then you can actually then go to, and it might actually stay in a static state on that, like happily, but not proliferate along the structure, but then like kind of stop. Or it could like proliferate and spread beyond it, right? And where the features now are really small, but the cell spreads powerfully across these domains. And you see that kind of structure shown from left to right, okay? And so that actually benefits the development of the so-called cellular workbench, and, where you have the ability of doing microfluidics and and assembly and targets and characteristic methods of characterization, which are either spectroscopic or sampling the fluid base, et cetera. And I'll skip that slide and just go to this one, that in more recent times, this has actually been raised to the level of three-dimensional architectures. So this is an example of the assembly of a mimetic structure of the dorsal root ganglion on a three-dimensional substrate, which is patterned with a recognition element, RGD peptide, which elicits where and how the cells, and this is like a multicellular structure that's needed for this, involving not only just the neurons of this excised tissue, but also the glial cells. So this is probably the most complicated case that I know of in the current literature. But the underlying structure is one that actually carries electrodes, so you can do the electrophysiology directly in contact with the structure, seeing how both the chemical cues and its topographical textures influence cell attachment, growth, and proliferation and function. And so you see characteristic data there of the electrophysiology that was done. Okay, so soft lithography continues to advance, and phenomenally so. And you can get access to all kinds of structures. But I want to actually point out that I think one of the best things that happened, in the full sweep of this work, is the ability to do printing in other kinds of contexts. And it revisits printing as a mode of doing microfabrication. So, for example, printing solid inks. And in work with John, the first exemplar was actually printing single crystalline silicon, where you do fabrication on wafer that's needed to get the electronic parts in the correct form, and then be able to do pick and place transfers using soft lithographic materials as the way of doing system level integration. And the idea here that's really kind of cool is that on wafer you can do dense fabrication in ways that take the thermal budget away from the atypical substrate. Like, so for example, if you have to dope a semiconductor by heating it at 1,000 degrees, you don't want to do that on Mylar as a substrate, because you won't have a substrate left anymore. So, but also because you can do pickup and put down in principle, you can do this with area expansion. So, for example, I could come along with a stamp which has a pixel layout that's some scalar multiple of the underlying substrate texture, where the device elements, and pick and place them in a way where you do areal expansion at the receiving substrate. And so now I have to show you a movie that shows how this is possible. There's a lot of physics on this slide, but I'll just indicate the part of it that's important by showing this movie. This is a log rolling down an elastomeric hill, okay? And what's really important here is that you notice that, contrary to what you expect, there's no acceleration, right? It reaches a terminal velocity, which is actually related to the energy dissipation rate. I think this is actually a macroscopic manifestation of entropy, because the energy dissipation is going somewhere. And that's like the really cool part of how elastomers work. And it has a characteristic velocity. And what you can do with that is, so I'll just go back one slide, is what you can do with that is that you can actually, rather than having just that static outcome, you can pick up slowly or you can pick up fast. And the way I analogize this is removing, a Band-Aid, a plaster, with or without the hair on your arm, and so you can actually define regions where you pick things up and you put things down. And, oh, I'm sorry, oops. Okay, and here's another example. So picking up and putting things down, this is a really sophisticated ink. These are gallium nitride blue emitting LEDs fabricated on a silicon-based substrate. So these are relatively inefficient LEDs at this generation because growth of these devices on silicon was not a well-developed technology at that time. This was a recipe that we developed that gave effective devices, but you can do pick up and placement with any kind of arbitrary expansion of pitch at the receiving substrate. And the example that we did with this is shown here, and that is to integrate these printed LEDs, very small ones, in conjunction with one of these microfluidic type things that are the voxels to contain a phosphor that shifts the emission from blue to white. Okay, and what's cool about this picture, if you look at the scale of it, you see a 10 millimeter scale bar, and you see the white light coming out of it. The total amount of semiconductor that's in this structure actually turns out to be the typical amount of semiconductor that's in a single conventional LED, right? So the way this thing becomes impactful is that it transforms the electronics design rule into one that's now more broadly articulated photonically, right, and optoelectronically. You can make it an optical design rather than a just semiconductor design. This was a commercialized outcome for a work of this sort, which printed gallium arsenide-based microconcentrator PV elements, okay, which the underlying cells were three-junction cells of very high efficiency, so 42.5% conversion efficiency at 1,000 suns, okay? So that's with light concentration. And the optics that are shown there are optics that are two-stage optics that are used to generate concentrations at that level, at that very small cell. Okay, and this is actually a device that's showing the device performance on a printed substrate that contains 500,000 of these microcells. Okay, and I still think this is the structure that has the world record for highest conversion efficiency in a concentrator form. Okay, and in terms of every characteristic of it was like remarkable, but because it's optical based, right? This requires solar tracking, right? It's a flat panel in the same way. In recent years, we've done a lot of work to look at this in other ways that get rid of the requirement for solar tracking, and that's like a part of the story I don't have time to tell, but. Pick and place transistors are actually kind of interesting with these elastomeric tools. So for example, you can print 3J devices on base substrates with registration. In this particular case, it's being done on germanium with an optical interface that's used to be the insulator, separate the conductors for a 4-wire cell rather than a 2-wire cell with no need to actually current balance between all the levels. It actually makes the structure resistant to the change of chromaticity across the solar period as the sun rises and sets and changes in the yellow content, right? The long wavelength content over the course of the day, and you can do that and wind up with devices that are for example, with high registration. That's what's like cool about this, right? You can do, it's not that you're just making things with changes of pitch, you're doing multiple levels of fabrication with registration level to level. And because you do, a 4-wire device, right, we've now simplified the growth of that structure because it doesn't have to be done monolithically with epitaxy across dissimilar materials, right? Here using for the small band gap material, germanium. And this device had a current efficiency at the level of 43.9%, right, which is a really profound outcome, especially in an academic context, right? And I think the thing that's really neat about this is that this scales for looking at all kinds of ways that you can actually find pathways for known semiconductors with known materials to do the equivalent of monolithic things that currently cannot be grown in ways that by doing this device contact expansion approach, where you change the number of bus level connectors to make that, reach levels where you could do, modules that would be, as high as 52% conversion efficiencies, okay? And that's with some tricks related to anti-reflection coatings as well. So there's a lot of like really cool parts to this story and a lot of really neat materials design. And one outcome that's actually kind of interesting is that some of these designs actually work to the scale of large buildings, where you can do, grayscale patterns that separate semiconductors using the window itself as part of an optical concentrator to convert some amount of the solar flux into useful energy, either extant at the window, for example, to drive a chromatic response, right, to shift whether or not infrared passes or is reflected, right, electrochromic, or for example, if you could do a bus level interconnect across the whole building to actually do, passive power generation. So it's an interesting idea to think about. The latter option, passive power generation, is perhaps too complicated. So the last part of the story I'm going to tell is one related to the uses by George and Dave to actually look at, the characteristics of SAMs again, most, microscopically in terms of this aspect associated with how they transport electrons, and to really answer that question deeply. And there's been a lot of really beautiful work done to do that. Right? So the fundamentals, whether it's, you have electrons or holes that are tunneling, and how the barriers in the gap form, and with what characteristic in relationship to the underlying molecular orbital structure associated with those particular compounds. And to relate it to complex transport characteristics, like, for example, that are seen in biological electron transport technologies, but also, to make connections, for example, with device-level technology such as OLEDs and things of that ilk. George has studied this using liquid metals as the contact material. So this is using indium gallium eutectic as a way of contacting a SAM to make a nascent electrical contact that has really high structural integrity and high reproducibility. That's actually kind of one of the problems in this, is how you make the top metal contact in a way where the data is understandable. And so, for example, using particular functional group, you can actually make molecular rectifiers in this way. So this data shows rectification using ferrocenyl groups where the rectification is associated with the redox properties associated with that chain end termini. And showing how it scales as a function of like articulation of that structure, like whether or not it's a ferrocene or a bisferrocene, and what the R value is associated with that electron transfer environment. So there's a lot of deep physical chemistry embedded in this. And in Dave's work with Paul, where they're using STM as a method of grafting structures in, right, explicit, electron transfer components. This object showing what appear to be, at least the level of single molecules, fluxional characteristics associated with that transfer. Right? So I think the story that emerges here is that we can make large-scale structures that have remarkable properties, but we can also make small-scale structures that have phenomenally challenging characteristics that indicate understandings as yet to be obtained, but that will be accessible using approaches of this type. So that brings me to the end of the story, and I wanted to actually show the last slide, which is a picture that was sent to Brian. That was sent by Brian Benton, who was my postdoc at Bell after he went to Columbia for his faculty position. Tragic story about Brian passing away at a very young age, shortly after getting tenure due to an aortic aneurysm. But remarkable physical chemist, and got tenure at Columbia very, very early in his career. But sent Paul Weiss this picture of something Dave drew. And I don't remember exactly why Dave was doing this. He was interested in hairpin structures, and that's shown at the top of that picture. But he was also showing an aluminum oxide mesoporous substrate that comes from anodization of the aluminum. You all have experience with this because your iPods and stuff like that came in colors, have that kind of anodized aluminum that had been dyed, right? To have those colors. But if you do those protocols in a certain way, they have like sub-wavelength sizes, and they're kind of cool, and they're nanoscale and stuff. And I think Dave was looking at that from the point of view of making gratings for doing surface-enhanced Raman scattering. I think that's what it was. And he was getting himself all worked up about whether or not, there should be, gold or silver used first, and et cetera. And it was before the, I guess, finite difference time domain calculations could be done or were conceivable. And Dave wrote, "I quit." And if you look really carefully at the bottom, it says, "Me too," and I sign it, Ralph. Yeah, we didn't quit. Okay, but so I'll stop there. I'm sorry I went too long, but I'm trying to cover things for 3 people, and and it's an enormous responsibility. And I don't think I did it, as effectively as I wish I could have, and I wish I could have been there. But I hope you have a fantastic conference, and if there's any questions, send me a line, and I will gladly not answer. Okay. All right, thank you. Thank you.